today we are glad to have also a very wonderful and committed meteorologist who will be also explaining to us what he has been doing in his area of specialization. Actually, he's the person of Mr. Samuel Owusu Ansah, who is a principal meteorologist at the Ghana Meteorological Agency, and he's also the head of the hydrometeorological unit, that's with the Research and Applied Meteorology Department. And he's currently also working with the weather research and forecasting model. And it would be nice as we are gradually drawing to the rainy season. It would be nice to also know how they've been analyzing the 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 usual flooding situations that we've been experiencing in Ghana over the years, and it will be good. So I see this topic to be very timely, especially as we are also heading towards the wet period. So at least we can all be alert and really know what is really going on. Are we to expect more rains, and what is the impact going to be like on our socio-economic activities? So, Mr. Samuel Owusu Ansah, we are glad to also have you. He's my senior, and I really know how committed and passionate he is about the meteorological phenomenon. And I'm sure we are really going to have a very rich presentation from him. So, senior, Mr. Samuel Owusu Ansah, I would like to hand over to you.
All right, thank you, Dr. Kalevensa. I hope everyone can hear me. Let me stop sharing the screen and then now. Thank you, and then good morning to everyone for having time for this section, to talk about the meteorological analysis of floods in Ghana. I'm going to explain some various types of floods and try to categorize them into. I'm going to give you the introduction of this kind of research that I have conducted together with other colleagues, and then also the aim of the study area. And then I describe the monthly rainfall patterns of Ghana, and then also describe the product and methodologies that I use, and then some statistical analysis for these two specific cities which I study on, and then also the two cases, that is over these two areas, that Accra and Kumasi, and then I also come up with my conclusions and then give you some references and acknowledgements. So, to begin with, we know that flooding has become a major problem globally. And when we are looking at the global level, that is from 1930 up to current, we have seen a huge increase in flood globally. And according to research, we could see that up to the last 50 years, 18 years out of the last 50 years have recorded serious flooding incidents within various countries, which has made it very, very significant for discussion, in terms of meteorological disasters, and then globally talking about other forms of disasters. We are really concentrating mainly on meteorological disasters. Economically, that is according to a certain site which is mainly responsible for capturing disasters that happen globally. An amount of 780 $6,500,000 globally amounts to the level of destruction that has really caused the whole world. And this one was up to 2014, meaning that from 2014 to current, it's even going to increase. When we zoom deep into Ghana, some of the major causes of flooding, as we all know, we have this climate variability and then climate change. We also have a poor physical planning and then flaws in drainage network. There are some possible causes of flooding within a country. But this particular topic that I'm discussing with you, it's on two occasions that we had floods, serious floods recorded in Ghana, specifically over Accra, and then also over Kumasi on the 28th, that's on the 18th of June 2018, and then also 28th of June 2018 in Accra and Kumasi, respectively. So records by Ghana, the National Disaster Management and Organization, which is NADMO, during that particular event, indicated that it led to 14 deaths. People died. They were drowned by these events. And then also about 34,076 others were displaced. And then also properties that were damaged amounted to about $168,289 US. And this was just those particular recorded cities. This is what was being recorded. So you could see just 2 days, this amount just going is a serious thing that needs to be analyzed and then used as a reference in the future. So as we can see, the heavy rainfall events has afforded us an opportunity to conduct this particular research, which I'm discussing with you now. So I really want to get deep into some few explanations of what we mean by flood, so that it will give us a clear picture of what I'm talking about. So we have about 5 different types of floods. So just like we can see over here, flood is generally defined as a temporal overflow of water over areas that are not normally submerged. And this is just the basic understanding of what flood is when we talk about flood. So like I said earlier on, globally, we are seeing this phenomenon increasing very significantly. And talking about the various types of floods, we have the fluvial flood. When we mention the fluvial flood, it's just basically a flood that occurs when we have the water level rising above the top natural water bank or artificial embankment. An example could be the Wager dam that was opened that flooded a lot of homes within the Wager municipality. And those of you who live around that area, you realize that it was really not convenient. That type of flood is called the fluvial flood. And we also have another flood type, which is called the pluvial. So you could see it's somehow similar, because if you look at fluvia and then pluvia, you might, if you don't get closer to the person even talking about it, you will not be able to understand what the person is trying to say, whether fluvial or pluvia. Let's be very attentive to that. Now, talking about pluvial flood, it occurs when intense rain causes rapid runoff that exceeds the capacity of any strong storm drainage system. So in this, I think this is normally seen in our cities. For example, we saw, we normally see around the Odo River and then some other river bodies. You know, when it rains, you see these storm drains not being able to sustain the volume of water that really get into it. So they tend to overflood. I mean, they extend and exceed the drains, and then they cause serious flooding, and then that leads to also people losing their lives or what is destroyed. So that kind of flood is called the pluvial flood. And then we also have the flash flood. The flash flood is mainly a mesoscale convective system that produces volumes of rainfall at a very short duration. So for that one, we normally experience it in Accra. And then we also have the coastal flood. The coastal flood occurs when we see storms coincide with high tides and then high winds. You know, for example, we saw over the Kita area, although we are seeing sea level rise, that is a coastal flooding. All right, it's also caused by this climate change, because we see sea level rise as a result of melting of what was the name, the ice caps in the polar regions, and then the trying to increase the volume of the water bodies, the sea level, hence leading to flooding over low-lying areas. And then lastly, we also have the groundwater flood, and that one occurs when the groundwater level above the surface, when the groundwater rises above the surface level, and then leads to inundation of low-lying areas. So the main concentration of this particular discussion is the pluvial flood and then the flash flood, which is dominated by meteorological phenomena. I just want to play this small video of Accra, whereby we see serious floods over this area. It's not okay. So this is just how flooding situation occur, especially talking about Accra. Okay, this video is not my own video. These are some snapshots of videos that really captured the various forms of, I mean, the rate at which the flood waters affect us. And then also you can see fields all over. And this is a common characteristic of Accra flood. And also some parts of Kumasi too, we can see such people being affected seriously by these flood water levels. It's something which is very common, but I think every year these things keep repeating, and we keep talking about it, and then when it's over, we just come back. I think we need to really do much work over some of these things, especially talking about these fields that really are being collected when we talk about flooding. Okay, so let's continue. Now, earlier on, I was talking about the increment in flooding situation globally. So let's pick 2 decades, 4 decades. So for the first 2 decades, that's counting from 1980 to 1999. That's the first 2, the last 4 decades. And then the last 2 decades, also from 2000 and then to 2019, the records of disasters that have been recorded. And you could see that for the last 4 decades, we had 4,212 disasters. And then in the last 2 decades, that's from 2009 to 2019, we had an increment to 7,348 disasters. And now let's move into the causes of some of these kind of disasters. We have different types. We have drought, earthquake, extreme temperatures. We also have flood, which is of our concern, flood. And then we also have landslide, mass movements, storms, volcanic, and then also wildlife. You see, out of these, you could see that for the last 4 decades, for example, you look at flood. Flood has 1,389 occurrences, okay? And then we could see that that same flood in the last 2 decades has increased appreciably to 3,254, which is very, very, very serious. And then when we also look at storms, which is also related to meteorological phenomena, that one has also increased from the last 4 decades, 1,457 records, and then has increased to a whopping 2,043, which is very also serious. Let's move to West Africa. That is where we find ourselves within the Volta Basin. Talking about these two diversities, that's from 1980 to 1999, and then also from 2000 to 2019. Just look at La Côte d'Ivoire. All right, the first case, that's from 1980 to 1999, increased from 2 to 12 occurrence. This is related to flood. Now Mali also having from 5 to 21 occurrences. Burkina Faso, 5 to 17 occurrences. Now we come to Ghana, 4 previously, and then now 20. So you can see that now the rate at which flood is increasing is very serious. So there should be an urgent address to this, or else it's really going to cause a lot of havoc. So let me continue. Talking about meteorological phenomena, you know, within our workspace as meteorologists, we have a number of things that we really look at. And these are what causes the various convective activities that we see during our monsoon period. So in this particular imagery, as you can see over here, it's just like it's a 3D one capture, a 3D description of what really goes on in the atmosphere from the meteorological angle. So you have the African terrain over here, and then we can see there is a certain line. This is a broken line, and we meteorologists call it the ITCZ, that's the Intertropical Convergence Zone, or ITB. The French call it FIT. Now, this is a meeting point of the monsoon. That's the moist winds that are coming all across from the ocean. They meet the dry winds that also come from the continent. So the meeting point is what really helps us to describe the propagation and the migration, the variabilities within our area in terms of the various tracks of convective activities seasonally. So in a nutshell, we could see that from the surface, you see over here, we have various heights that have been calibrated. So meteorologists use pressure levels to describe these. So for example, when I pick from the surface, normally we normally use these terminologies like at the 850 hectopascal level, at the 700 hectopascal level, and then moving up to 200 hectopascal level. All these things are various altitudes that we take into consideration, right? So looking at this, we can see there is a monsoonal flow, right? A moist leading wind, which meets the dry winds. And about 1 degree below this particular meeting point, we see convective activities. And then these convective activities are controlled by wind levels at these various altitudes I was referring to. So the dynamics that really play, the dynamics that really comes into consideration when we talk about the state of these convective activities is what we, the meteorologists, analyze to be able to understand what is really happening. So this main research, as I told you earlier on, is to understand the meteorological conditions that led to the flooding events that occurred over Accra and then Kumasi for the 18th and then 28th June 2018 respectively. And then the other aim is also to document the findings for operational and then research purpose. So those of us who do not know, especially our foreign partners who do not know where Ghana is in West Africa. And you could see from the study area, we have the map of Ghana being brought out, and then the area which we are trying to do our analysis also being brought out. So Ashanti region, that is where we find Kumasi, and this is an imagery of that particular day that was captured. And then also in Accra, we can see another place also captured. So a brief description about Ghana. Ghana, as we can see, is located between latitude 4 to 12 degrees north, and then longitude 1.5 east to 3.5 west of the Greenwich meridian. The climate of Ghana is dominated by wet and then dry seasons, just like I was describing in the previous imagery. The meeting point of the dry air mass and then the moist air mass determine the seasons of our country. So in the northern part of the country, there is this description like unimodal rainfall pattern, which simply, I think in the next slide, I'll be able to explain that. And then we also have in the southern half of the country, minor rainy season and then the major rainy season, also constituting a bimodal rainfall pattern. So just like I was describing earlier on, the monthly rainfall pattern over Ghana has been described. And we can see along the coast over here, made up of Ada, Takoradi, South Pond, Accra, Tema, and then Axim, we can see that we have two peaks. We have the major season peak and then the minor seasonal peak. and this is a monthly distribution of rainfall. And when we say bimodal, that means that this is what we mean, bimodal pattern. And then when we move to the middle part of the country, we can see also two peaks. We have the major around June, May, June, July. Then we also have the minor around October. All right, we can see there is one particular time series which looks like it's just one. And that one is a unique location within the middle part of the country, which is called Kitikrachi. It's because of the position. Kitikrachi is the location where it is. It has a certain characteristic like the northern part of the country. When we move to the northern part of the country too, we can see a unimodal that is just one peak. All right, so that is what we mean by this bimodal and the unimodal. The data set that was used in this particular study included about 45 stations that GMET observed rainfall data, that stations, GMET, and then also we used some product, which is a global product called the Global Satellite Mapping and Precipitation. We also used the WAF research, the weather research and forecasting model, which is the WAF model. Yes, GMET is running that. Currently, it's down, but during the time that this was conducted, was in operation. So we use that one. And then also, we also use a system called the Synergy, which is made up of different forms of models that is being run over Africa and the entire globe. We receive images or model output from France, from UK Met, globally. So it means that it's embedded in it, and these are products that we use in doing our studies. Okay, so this is the methodology that was applied. We did interpolation using the IDW method to generate rainfall interpolations over the entire country. And then using the GSMAP products, we generated hourly propagations of the system to help us track and then understand the propagation of the systems. And then we ran the WAF model to mimic these particular two cases, and then to be able to understand the underlying systems that really contributed to the flooding events. And then we also did some few statistical analysis using the extreme, generalized extreme value to fit the distribution over these two areas. So a time series of the rainfall amount that was recorded from 1960 to 2018. We didn't do it up to 2020 because as at that time, we were not in 2020 yet. But we could realize that the total amount of rainfall that was being recorded annually, this one is the annual daily maximum rainfall. All right, so for a single day within one particular year, the highest amount that was recorded is what has been drawn over here. So you could see so far there is an increasing trend for over Accra. We could see that the highest rainfall that was recorded, it was starting from 1973. We had about 175.3 millimeters of rainfall that was recorded during that time. And then in 1995, which I quite remember, I also experienced this particular rainfall, 243.9 millimeters. So far, according to this record, is the highest peak, the highest amount of rainfall recorded per single day. So, and when we look at this trend, and also we have in 2015, when we had 212.8 millimeters of rainfall, that was also recorded per a single day. And you could see the trend is increasing, which raises, it raises concerns, because this analysis is something which is eating into the future. So we need to take, the necessary cautions. When we look at that of Kumasi, in Kumasi, we are seeing that the trend is rather decreasing, and the peaks are not as huge as that of that in Accra. And all these things would be as a result of the geographical locations of these two particular cities. So Accra is along the coast, while Kumasi is within the forest zone. So there are a lot of significant difference in these particular levels. Now, we also did a frequency analysis using the 95th percentile of this analysis. And then we realized that in Accra, it's also decreasing. All right, Accra is decreasing, and then Kumasi is rather increasing. So there is something very important that we also found over here. We are talking about the maximum rainfall per a day for every year. We'll come to that. So let me zoom into case A, that was for Accra. This is the global satellite precipitation measurement, global satellite precipitation measurement product, which I was mentioned earlier on. And this describes what really happened in 2018 on the 18th of June. You could see the system develop over here. Now, over where we see the very high red areas, that is the core of the system that really propagated along our area. So you see, it was located initially over the coast of Benin, and then it just moved in and then just traveled along the coastline and then also tracked around the coastal areas. And this really bucketed a lot of rainfall over our area. So the accumulated rainfall for that particular case was this. So at the end of that day, this is what we recorded. So you could see Accra had some serious rains, although we didn't talk about some other locations like the Salt Pond. Salt Pond has serious rainfall over that area, which was even huge, and that was what was recorded over Accra. However, because our concentration is just over Accra for now, this is the total amount of rainfall that was recorded for that particular day. And the impact during those that period is what we can see over here. We have that in Kwame Nkrumah circle, and then also Kaneshi. I think the number of deaths that was even caused, Ubateshi, the Adentine environments. In fact, a lot of places experience this kind of flooding events. Okay, so from the meteorological angle, you know, in GMET, we use this system I mentioned earlier on, the synergy. This one is from the Meteo France, and it tells us the various pressure systems that really led to this dynamics we are seeing. Now, over here, we see these values. These are pressure values. We have the Azores, we have the St. Helena, we have the Mascarenes, and then we also have the Arabian High. These are the systems that control, the pressure system that control our rainfall pattern within our terrain. And we also have something we call the equatorial trough. This is very significant from the meteorological angle. So whenever this particular pressure system intensifies, when it intensifies, definitely it will push more moisture from southern part of Africa inland. And then in that case, it affects the position of this pressure isobars. It is around 10 hectopascal. That is the isobar we are talking about. And that is what we call the equatorial trough. And this thing, as at 12 in the afternoon for that particular fateful day, this was the position. And you could see in Ghana, we were just being hovered around over by relatively higher pressure isobars. So we see 10, 16, 10, 14, and then it goes on to 10, 10. So now what happened in the evening? In the evening, there was an expansion of this equatorial trough, as we can see over here. And in that case, you see, there was a relaxation of the various isobars, the various pressure systems. And this also contributed to more moisture being drawn in, and that led to this phenomenon we saw over here. So we also ran the WAF model. Over here, what we can see is the 850 hectopascal relative humidity. The winds at 850 hectopascal from the WAF model. This was very significant for operational purposes, because we realized that the system was sitting over here. This one is at 12 p.m. And at 1800, according to the forecast of the WAF model, we also realized that there were intensification of this particular wind pattern, which led to more favorable conditions for the system to thrive. So just like I was saying, what I showed you earlier on is just the 850 hectopascal. Now at the 750 hectopascal level, which is our 3,000 kilometers deep into the atmosphere, this is how the behavior of the wind pattern was. So over here, the winds were, there were some convergence trough, which really led to the sustainability of the system. So at 1800, this really intensified and caused more favorable conditions for this particular system to develop and track over our area. This is at the 200 hectopascal level. And that one too, we could see very strong subtropical jets that really helped the system to also survive. And that at 1800 too, we could see its dominance. We also did that of the ascents, vertical ascent. Mostly we have the dry adiabats and then the moist adiabats. So at the surface level, we could see there was some level of dryness over here. This is more meteorological. So the meteorologists would understand this one better. So over here, we can see some separation of lines here, and that is at 12 o'clock. And we could realize a number of, dryness. And then when you move up into the atmosphere at the 850 to the 700, we could see some camouflage and some level of meeting points, like there is an overturning. So this is a significant phenomenon for we the meteorologists to understand what is expected. And at 1800, that is when we saw this this system that was being monitored over Accra, generating intense moisture to support the system. So to help us understand the various dynamics that really pertain to this particular system, we used, I think, a research checklist called the Miller checklist. And these things are very important points within the ascent which I showed you earlier on. Talking about the surface pressure, the dew point pressure, so the dew point level, then the convective available potential energy, and then also the mean relative humidity that really pertained during that time. Yes, looking at that and comparing to the Miller check list, which gives us a condition of weak, moderate, and strong. So in categorizing this particular phenomenon that occurred in Accra, this is what we realized in putting it together. The surface winds were above 10, so the surface pressure was 10 hectopascal, 10, 15 hectopascal level at 12 and then 14. So when we look at the weak category, you could see that it's above, the weak category says that surface pressure is above 1010. And 1010 is within this particular category. And when we look at the comparison from the other parameters we are talking about, we will see that most of these systems were within this particular category, right? So the system that we saw over Accra that caused this flooding was a weak system, because the dynamics within the atmosphere caused the slow movement of this system, and that led to more rainfall, which led to the flooding. A similar analysis was also done for the Kumasi area, because it's the same thing that was done, so I wouldn't really spend much time over here, but you could see over here in Kumasi, that is where we saw the system disturbing and then causing a lot of havoc over that area. And it has been tracked by this particular system. So this was the total accumulated rainfall that was made during that day of Kumasi. And then the impact over this particular area is what we can see. Angloga, and then Asokwa, Asokore Mampong, Asafo Market. In fact, these are just some few pictures which really emphasize on the impact of the rainfall that has traversed. And also analyzing this, we could see from the meteorological angle, most of the time we are very technical. Some of these things, the meteorologists would rather understand. For our people who are general users, I believe some of these things really, it wouldn't really bother you as much. But the most important thing is looking at the various parameters that have been analyzed over here. We are able to see in advance what the system is going to do in the future. And this one was at 1800. Just like I explained earlier on, we have the equatorial trough also expanding, and that act alone has gives an indication that yes, there is going to be intense rainfall in relation to it. And then we also talked about the WAF model, which was also run for that same particular day. And over here we could see troughs or vortexes seen along these areas, and these also contributed to the system also becoming intensified. So it's similar to what I showed earlier on over Accra, just that this one was deep within inland. Accra's own was over the coast. So these are the various wind levels at the various heights at 850 and then 700 and also 200 hectopascal level. And a similar thing was also seen for the T5 which is also the ascent, which helps the meteorologists to be able to understand the moisture level within the atmosphere and then are able to predict what is expected in the next few minutes. Okay, so the Miller-Check list was also applied again over here, and then during the comparison, we also realized that that system was also weak. So in summary of this whole discussions, we did an investigation of the meteorological dynamics that underlined the heavy rainfall that resulted in floods over Kumasi and Accra on the 28th and then on the 18th of June. And then also we did a meteorological analysis to confirm the thunderstorms status, whether it was weak or it was strong, conditions that were really surrounding it that led to the propagation of the system. That was what we discussed. And then also, we realized that the main synoptic features, although you see, we were using global models to do this analysis, but unfortunately, we couldn't see some significant features in the synoptic domain to help propagate this particular system during the time that this was happening. I was in the office when this happened, and we ran the WAF model, and the WAF model was rather able to capture the various dynamics that really supported the system. So it was a very good thing for us using the WAF model to do forecast operations. So, so this study has shown the main synoptic features that produced the heavy rainfall event in Ghana and could serve as a reference for forecasters, both in Ghana and then also the West African sub-region. So in conclusion, we realized that the phenomenon that really caused this heavy flooding, as we were showing, as I showed, was as a result of anthropogenic phenomenon, meaning they were man-made because they were not meteorological. When I talk about anthropogenic, that means the things that prevented the flood, the water to move to where it's supposed to be. The poor drainage, also trying to build on waterways. These are the things that really contributed to that particular phenomenon. And we realized that there was some significant threshold that was recorded over both cities. When we did the frequency and the 95th percentile, we could realize that in Accra, we have 45.1 millimeters as a threshold. And then in Kumasi, we had 42.1 millimeters as a threshold. So it means that such an amount is not very significant for us to see flooding within our vicinity. But because of our planning issues, because of our improper disposal of refuse, because we do not do rooftop rain harvesting in our urban areas, some of these things really contributed to has contributed to this kind of flooding that we normally see of late. And God being so good, now GMET is using something we call nowcasting. We now have some products which is helping us to be able to do nowcasting to help predict possible flood events that could occur. Immediately we see it. And now our kind of forecast that we do is impact-based forecast. It helps us to be able to explain the level of vulnerability and then the impact that is going to hit on the, on our assets and then the populace and everyone. So right now, we are also having another facility, which is called the My Flood Risk Accra app, which also helps determine the possible chance of floods within our terrain. Unfortunately, it's just over Accra, that's Greater Accra Metropolitan Assembly area, and then also Ga East and then Ga West. These are just pilot areas. There's a plan to do an expansion of this. These are new tools that we are using to also help, educate, or let me say, raise awareness over the general, for the general public to also be sensitized by any possible flooding event that will occur. So these are just some few references, and then these are some acknowledgements that I would want to show. We have some giant GMS staff, some who have retired, others who have also left to do further studies. Yes, they helped in this particular research which I presented today. Thank you. But I can see a number of, a number of questions that have been raised here. So I think one was saying he cannot hear the sound. I think that one was the earlier problem that I faced. And then there's also another one. He said, please, the types of floods we have, the fluvial, coastal, groundwater, please, what is the last type of flood called? Okay, that is the groundwater. Let me go back to my slides to show that type of flood. Okay, so we have the groundwater flood. That is the question that someone was asking. Okay. And okay, there's also another question here. It says, is there a way to issue rainfall warning effectively? For instance, an app or some effective means during rainfalls. I am always confused which way to drive to avoid flooded areas in Accra. All right, thank you. This question, I think I made mention of my Flood Risk Accra app, which we can download to also support this awareness in terms of like the alert, because whenever we are able to see, whenever we are expecting any major system to occur and then cause rainfall over our area, there is a push notification given to all users who have downloaded this particular app. It is called my Flood Risk Accra app, which is used to alert people over these piloted areas, like I said, the AMA, the Ga East, and then Ga West. These are areas which you can easily receive this flood push notification. I think there is no, I've exhausted all the comments that have been raised over here. Okay, I'm now being my own moderator. All right, so I can see Mr. Jacob Ejekum. Please, can you unmute yourself to ask a question?
Hello, good morning.
Good morning.
Thank you very much, Sammy, for the presentation. I have some few concerns about so when you were showing the time series for I think the maximum rainfall amount from no, I think that's yes from 1960 over Kumasi and over Accra. Um, maybe I was just thinking about. You see, this study was for Accra and Kumasi for just one case.
Yeah.
Okay, one case each. Yeah. So if we could look at the years or the years that reported the maximum rainfall. I'm sure if you do a standardized deviation, you'll get more years with maybe rainfalls above the normal. So that maybe we can look at the meteorological analysis for all these extreme cases and then maybe compare them and have a benchmark for more sort of a climatology for Accra and Kumasi. It just came to mind, and then I think maybe not just for these two cases, but if you could look at all those cases within 1962 to present, maybe that's also going to be interesting to look at.
Oh, okay.
So and then my question is how are you going to use all these statistics when it comes to maybe forecasting? Are you are you able to do this before maybe you bring out impact-based forecast? Or I was just thinking about how quick you can actually run through this analysis before you get to the forecast.
Okay. Thank you very much for the question. Now, this analysis you are seeing over here is a climatological analysis. At least as a forecaster, before you issue any forecast, you should have a background climatology of the area you are dealing with. So this is just two spotted areas which have been used as a case study. So to understand the amount of rainfall that is possible for a single day, all right, the highest for every year. So you're able to understand what really this particular area is normally noted for before you be able to do your forecast, because there are a lot of things that you consider when you are doing forecasting. We normally consult different models globally to be able to understand what is expected, right? And then we also use satellite imageries as well as something we call the now casting, which is a facility tool, NWC SAF, which is a facility tool for monitoring systems that propagate. So just like you were asking me, we do have this analysis as a background check to be able to help us in the future. When we looked at the system that propagated over Accra, you could see that over here, there was a certain characteristic which we can use as a reference, because our systems come in different forms. But when we see something of this nature, we are able to now link it up to what has happened before. And then based on that, we'll be able to come up with a very good judgment of what really transpired. So it's not just only the satellite imagery, and it's not just only the models. We use also satellites. Sorry, we use also some facilities that we have in-house over here, like the NWC SAF, which I mentioned earlier on. So as a forecaster, you need to have all these things. You have to have these things at hand to be able to help you do a proper analysis. Hello, Jacob.
Yeah, it's clear now. So I was thinking maybe how on the meteorological analysis you have done, not considering the other products you mentioned, but it makes sense that you are considering all these products to come up with a forecast. Thank you.
All right, thank you.
And then on the okay, yeah, I thought maybe that was a suggestion. Maybe we can talk later. All right, thanks.
Okay, okay. So I don't know whether anybody also has any other questions to ask. I think my moderator is offline, so I'm doing my own moderation.
Yes, hello.
Yeah, hello.
Yeah, well, that was a very good presentation. So I have some few concerns.
Okay.
The case study, both the case studies A and then B, comparing to what you talked about on the Miller, is it table?
Yeah, the Miller checklist.
Miller checklist, exactly. All right, so looking at the values that they were given for a strong system. Okay, yeah. So looking at a strong system, they are talking about pressure levels less than about 1,005 hectopascal, right?
Yeah.
But on both the case studies A and then B, realize that having very high pressures along the coast, especially in Accra, between 1016 and then 1014.
Yeah.
And then also for the case study A, the pressure were ranging from 1014 and then 1012. But then we're able to get very high rainfall values. I would like to know what accounted for that.
Okay. You see, this the high pressure level, like we saw over there, you know, it inhibited the propagation of the system. You get it? So because of that long duration, it will also lead to more rainfall over, you know, as the system is moving, you know, it's just releasing a lot of rainfall. But if it's moving very fast, you release, you receive less. But if it's moving very slow, then it's going to take a long period for it to, you know, before it can move to the next location. So the high pressure inhibited the movement, and therefore it caused more bucketing over specific areas, right? So it's very significant. I think during the rainy season, when we normally see low pressure zones, we feel like, yes, the systems are going to track within these low pressure zones, which is okay. But when we have high pressures also approaching it, it also causes, it depends on the strength of the system. It causes a number of, you know, what's the name? It inhibits the propagation. Therefore, it affects the, so for us, inhibiting it, it causes more rainfall to be realized over specific areas for a long time.
Okay, thank you.
All right.
Hello, Sammy. Sorry, a follow up on the
Hello.
table.
Okay.
Do we expect all these conditions to be met before maybe we can have a strong, moderate, or weak, or maybe one of the parameters we could have the maybe a higher cape that the pressure, as you explained, maybe inhibiting the propagation of the storm. So we have the storm concentrated over one area. Is it that you have to fulfill all these requirements before we can have a weak, moderate, or strong? I just wanted to.
Okay. You see, all of them are very significant. All of them are very, but you could see pressure really played a very huge role over here, right? So you could see not all the conditions were satisfied to categorize it into the weak, but there were some which were very strong, all right? So that is what led it to that particular categorization. Hello.
Says, from his Owusu Ansah submission, I think he channeled that pressure values based on the model, the satellite model. He cannot, based on the satellite model, is what actually induced that pressure values, unless he has to come clear that these are the pressure values that was recorded specifically at the station.
That's what I.
One reason being that. Kwesi, should I go ahead?
Yeah, go ahead.
Yes,
Hello.
yes.
Sorry. I think my laptop.
We want to find out. We want to find out for now if these pressure values you were getting are pressure values recorded at the station where these rainfalls, this accumulated rainfall was gathered.
Yes, please.
Or it is a pressure value on the mesoscale level. That is from the models you were introducing to us.
All right. These were the records that was observed for that particular day.
For those stations?
Yes.
Station measurement.
Yes.
So then if that is the case, I think we should also take a look at the pressure values. The reason being that I don't know whether you use Kumasi, the synoptic station, as the airport synoptic station, because we all know, I mean, atmospheric pressure varies as and when you go to places. You can have atmospheric pressure, perhaps if you use the airport station as your reference point, we can have atmospheric pressure around 10-15. When you move from the airport to, say, a Crowfrom area, or let me say, Abreport Junction area, you might have a pressure value quite different or varying from that of the one recorded in Kumasi Airport. I don't know whether I get you.
Yes.
Can I come in?
Yes,
okay.
Okay. I don't know when exactly the rains occurred, the time period within which the rains occurred. But
sure.
One thing I know is that before I will read is over the place at that time, the rains, pressures increase. I hope you understand.
Yes.
Pressures increase at the time of rain.
Yes.
Exactly, because in that case, the atmosphere is very heavy, and therefore pressures in half ascent of air mass into the atmosphere. Pressure is low. But when there's pouring down, pressure is high. So before the storm reaches the station, pressures reduce. That is why I'm saying I don't know the time within which. So I don't know these pressures, 10-15, the 10-15 and 10-14 that we are seeing for Accra, whether they are the time of the rains or time ahead of the storm. I mean, before the storm got there, that we, if you can get us pressures ahead of the storm, before the storm reached that place, I think they will be far lower than these 10-15 and 10-14.
Yeah, I think you have made a reasonable point, and we will definitely have documents to back this particular pressure, because it looks as if, like you're saying, these pressure values are quite confusing with, in relation to the storm. But like you said, the time will actually draw a conclusion to it. So I think 2015, I'll also go into my archives and check.
It's 2018.
2018, yes. I think I'll have the DR to that effect. So I'll also check, and then if there's any.
Hello, Mr. Ansah.
Yes, okay.
Mr. Muller would like to say something.
Okay.
Okay, Mr. Muller, go ahead.
Yeah, what I'm understanding now is that at the time of rain at the coast, pressures were about 10-16. And as for storms, when storms are moving from the east towards the west, and pressures ahead of them, of the storms, are more than 10, 12, 10, 13. If we get 10, 14, 10, 15, the storm will break down. But if it's from the sea, you see, the sea will have a lot of moisture on land. So the rains can just start before even the thunderstorm sets in. So with that, it could be possible if the actual records, actual pressures taken at that time, it says that it is 1016, 1015 at the time of rain. Then the rains have actually started with the moisture in the system before the incoming of the thunder cell into it. But when it's from the west, I mean from the east, Nigeria, coming towards Ghana, with 10, 12, 10, 13, it can come, 10, 11, 10, 10, it can come. But 10, 14, 10, 15, with the storm not having strong winds more than 34 knots, the storm will break down. It will not come to Accra, or it will not break through the 10, 14, 10, 15, 10, 16 pressure, no. But if the coast is so much saturated, then the rain started, then it will continue to fall, and that will make the pressure go up at the coast. This is what I can say from my experience working at the coast for some time, or forecasting in the country for some time.
Yeah, thank you, Mr. Muller. That's great. You know, he's really an experienced forecaster, you know, on this, and I'm very happy for his contribution. Yeah, I think.
Hello, Mr. Ansah.
Yes.
Can we take a look at the 700 level once again?
Okay, just a minute. Okay, let me see. Okay, so have you seen the 700?
Similar. Let me see. Okay, so I think there was a wave trough that sustained the system.
So that trough sustained the depth. You see, the depth, and then the trough. The trough was bringing in. The trough was bringing in a lot of moisture. Wave trough at 700. There's no way the rains will not come.
Okay, so Mr. Ansah, with the 700 level, we are seeing this wave trough, just as you mentioned. This for the case study A, the rains that occurred in Accra.
Yeah.
So this also supported the massive rains we had on that day, even though the pressures were high. But then the wave trough at 700 levels sustained the system.
Yeah.
Yes.
To, as you were mentioning.
Yeah. So this is a classical thing.
Okay, thank you.
All right. Mr. Jacob, I think you raised up your hand.
Yes, I mean, I think it all has those Miller's checklist pre-storm conditions, I believe.
Yes.
Not during the storm. So some of the discussions we are having might not apply here, because I'm thinking you were looking at the conditions before, because we can see 12 noon. On the 28th of June, the storm actually started somewhere around, I think, 3 or so, if I am correct.
Okay,
I was in
case 2.
Yeah, case 2. The storm, the rainfall started on the 28th.
Can I?
So I believe some of these conditions that you have listed, you don't have to necessarily fulfill all the conditions. If you want to go list by checking the fulfilled condition, we might not be able to get a grasp of what the study is really about. So I think on these conditions are before the storm or the rainfall actually started. If Sammy, you could clarify a bit on that, that would give us the clarification.
Okay, so this Miller checklist we are talking about, you know, they had, I think there was a paper that was written to you know, point out the details of what have been happening, right? Mostly when we have convective systems. So these conditions, like you were saying, it's not so rigid. This is just a reference, a little reference for us to help us predict what is ahead of us. You get it? So there might be some conditions that are being satisfied. Yeah, but not every condition can be satisfied to maybe specifically. You could see over here, we have pressures greater than 1010, all right, which satisfies this first one. Now we look at the dew point temperature. This one is saying that less than 2.8, but over here we are seeing 21 and then 22 degrees, which does not satisfy this. When we look at the 800, that's the Cape, the amount of Cape, according to this one, you could see we were having higher Cape values over here, which does not also fulfill this particular one. But when we come to the RH, you could see RH was 80% for this one. All right, and this one we could see 90 and then 80% also for 1800, right? So then the winds too are also satisfying it. So based on these, you could see majority of it was in line. All right, that is how come we categorize it in this particular category. So the more we use it, the better it becomes. For now, I don't know whether any of us have used this particular checklist before on the operational level, but based on this, I think we should use this one as some guide to help us in the future. And the more we practicalize it, it becomes we become very used to it, and then we're able to give very good predictions.
Yes, Mr. Owusu Ansah.
Yeah.
Yeah, I think I have some, I have a data to buttress that of the point Mr. Muller made with regards to the fact that the rain started before the thunderstorm. And of course, in front of me, I have the weather notes in the year 2018, the month of June.
Okay.
That is 28.
Yeah.
And then it's 28, where the supposed flood in place, yes. And then it reads as generally cloudy conditions, continuous light rain started without thunderstorm, started at 16:07, that is 4 p.m.
Okay.
Moving into moderate continuous rain at 16:20, and then to a heavy continuous rain at 16:31.
Okay.
So at 16:43, that is when we had the thunderstorm. So
okay.
We had the thunderstorm with heavy rain, 16:51, and then the intensity fell to thunderstorm with continuous moderate rain at 17:06. Then back again to thunderstorm with continuous light rain at 19:19, and then to continuous rain again at 20:20. Then the thunderstorm had left. So continuous rain at 20:20, and then continuous rain, slight rain to 23:15. So I think what the point Mr. Muller raised actually confirms what actually happened, that the rain started earlier because the atmosphere was actually saturated before the emergence of the thunderstorm. So I think it makes sense with regards to these information and fact and figures on the ground. Yeah, that's it.
All right, thank you so much for your reference. And then I think it's a very good point. You know, mostly when we are doing this kind of researches, we need more information about the and on the ground proof to be able to help us very, very well. So I think, Kwame, I'll contact you for more of the information, because this one is really over your area, especially if it comes to that particular case. So I'm happy for
sure.
the contributions you have made here.
Sure.
I don't know whether anybody has any other. I think there's a question. Someone has raised his hand. Okay. It's Kwame. Your hand is still raised. Okay.
Let me just lower my hand.
Okay. So any other questions or any other contributions? It seems today I'm doing my own moderation. I think there's a question. Okay, somebody has opened. Paul Okra, please, can you unmute yourself too?
Okay, sorry, I'm sending you back. I wanted to get like the clear difference between like the types of floods we have: the fluvial, the groundwater, coastal, and the flash flood. I wanted to know their differences. So can you go back to that slide, please?
Okay, just a minute. All right, we are there.
Okay, so I wanted to know the difference. Their differences. Maybe you can give me the deep insight of the explanations.
Yeah. Please, can you raise up your voice a little? It seems you are a little low.
Okay. I wanted to know their differences.
Okay.
Differences.
All right, all right. So just like I was saying earlier on, for example, let's use these ones as reference, like the one in Wager, the Wager dam burst.
Okay.
It's not dam burst, like the release of water from the dam. It caused a lot of flooding over that area, the suburbs. So that is what we refer to as the fluvial, right? Okay. And then when it comes to the pluvial flood, that one we know it's as a result of normal heavy rainfall, right? You know, the storm drainage are not able to accommodate it. So it just tends up to enter into the streets. Okay. So and then also the flash flood, that one, like so this presentation, I will send it to all our participants to be able to also access it and then use it. Yeah. So in the meanwhile, you could see for the fluvial flood, that one, it is not meteorologically induced. You understand? It is not meteorologically induced. But for the pluvial flood, it is meteorologically induced. Okay. Is it clear?
Yes, please.
Okay, all right.
And then I also want to know, let's say, flood is a type of or an example of an extreme weather event. I wanted to know how we can mitigate the harms caused by flood as individual stakeholders.
You wanted to, can you repeat the last part again?
I wanted to know how we can mitigate the harm caused by floods or other extreme weather or other extreme weather events as stakeholders. How we can reduce mitigate the dangerous impacts.
All right, thank you for the question. You remember I was mentioning of the My Flood Risk Accra app. All right, this is just a pilot app. There are a number of precautions that are also embedded within this app. So for example, this uses, when you see any flood alert and you go in there, you would see a number of advices that will help you. If you need to evacuate from your area, then it will alert you that if you go by it and it's something that is going to really cause any casualty, because you have responded to these kind of advices, it will mitigate the impact over that, over the area, or so over you, especially the life that is also really more of concern. So if you listen to that one will help you to be able to also reduce the casualty level, right? Yeah, but apart from that too, I think people shouldn't be building on waterways, especially, these areas where we know they are flood prone. People are paving over areas, preventing lawns and here and there. So you see, it's our activities that really leads to this kind of conditions that we find ourselves in. Littering, it's something which is also of much concern. If we reduce such things, the users or the user community will feel free, will find life very easy to also, if it comes to drainage, if the government is able to construct very good drainage, it's also going to help us, mitigate this kind of impact that the flooding will have on us, as well as also the city planners. So everything is more of like a web. It's like a net, which we need to really go by to help mitigate this kind of impact that we normally see. So that's what I can say for now.
Okay, thank you. I also have my very last question.
Okay.
And does urbanization lead to the rise of flood situations? And then if yes, then why is it that in the rural areas we also encounter some flood?
You said rural areas, and then you also said urbanization. Urbanization, if it is not well planned, that one there, I'm telling you, because when you go to the advanced countries like Holland, all right,
okay,
it's an urban area, and then they have planned very well. They have put very good drainages, all right. So there's no way you are going to hear of flooding within these areas. In the rural areas, you could see there's no proper drainage too. You understand? If there are very good drainage, all right, it will also reduce the impact of flooding. So if you ask of why we do have flooding in the rural areas, that one, I think I've answered that section, because we know we need to get very good drainages to help. Yes.
Yes. Let me add a little to what you are considering. Considering the rural areas, I mean, urbanization is one of the major causes. In spite of the planning, you realize that in the rural areas, because there's no much pavement, there's no much tiling, there's no much, so let me say, the fact that they are not actually developed, let me use that word. You realize when there's any downpour, there's this choke, or let me say, this vegetation serves as a sink. You know, when you have an area covered with grass and an area covered with, let me say, a solid, or let me say, a hard floor, you realize there will always be this runoff. But then it's difficult to have a runoff at an area covered with vegetation. So one of the long-term advice we always give is that, I mean, instead of bringing on tiles, doing pavement breaks, whatever, it's best if we stick to lawning. I mean, bringing on lawns, planting of more grasses, even in our households. That will prevent, or let me say, serve as a mitigation measure when it comes to flood. Specifically talking of flash floods and whatsoever. So I think urbanization is one of the key causes. But then, in spite of that, if we stick to proper
Yeah, hello, Kwame. I think your line is off. I don't know. I think his network is misbehaving.
He made reference to what we need to do as stakeholders or as a country is that we do a long-term planning. Talking of long-term planning, you know, when it comes to this nowcasting whatsoever, my flood risk account, they are there at least for a temporary measure. Because if there's any approaching storm and then we give you the update, all those who are located at a flood-prone area will definitely experience this flood. And then if that occurs, definitely they will be displaced. So a long-term planning goes beyond meteorological advice, and that is when the government and the law enforcers will have to come in. Because if we give room for people to just build anyhow, if we give room for engineers to construct any roads without considering storm drains and let me say storm trenches, I think we will continue to be facing this problem of floods every now and then, because the rains will keep coming. You cannot stop the rains from coming. So I think that is what I have to add to that of Mr. Owusu Ansah's response to my colleague.
All right, thank you so much, Kwame, for your input. Ralph, do you want to talk?
I think Kwame didn't get the question he asked. I think he asked about flooding being caused by urbanization, and he's asking why then do we have floods in.
But I think I answered him by telling him that in the rural areas, you know, definitely people, they don't actually build like the way that of the cities. Everybody wants to build in the city. The city is being choked. So definitely there are little or less lands And definitely these less lands are occupied by people who are coming into these urban areas. So it boils down to the fact that lands are being sold even if they are not supposed to be sold. And then these lands are served as
so he says why do we have floods in the rural areas?
Yes, we are not having floods. It boils down to the fact that why do we have floods in the urban areas?
Why do we have floods there? No. Is it why do we have floods in the rural areas? That's the question.
Mr. Muller wants to come in.
Hello.
Hello.
Yeah, we can get floods in the rural areas. The rural areas, they have rains, and at certain type of the seasons, we have more rains than we expect. And that can happen because something, Mr. Ansah, you know about this, return periods. A period the amount of rainfall that we may get at a certain village or place will be about 3 or 4 times what we normally experience. At Adan, for instance, in 1968, we had flooding there. 1972, 73, I was in school, we had flood. It's a sunny area, but there was flood. And I think in the 80s, when I left there too, they had flood there. It depends on the volume of water, volume of rain, the rainfall amount that comes in at that time, which exceeds the normal rains that occurs over there. So when I was young, I was thinking, why should a sandy area get flood? So when I did I came to Meteor and I saw that with water resources management knowledge, you know, with these aquifers and all those things, they have their limits. So if the volume of rain comes, the recharge comes and it's beyond the discharge, you still have the floods occurring over the place. Rural areas can get flood if the volume of water or the volume of rain which is falling exceeds the normal one which comes over some years. It can come at maybe submitted about 10 years or 20 years, and then we'll see it once. That sort of return period. Thank you.
All right. I think we could go on and on and on and on because it's becoming more interesting. Yeah, but I am thinking that because of time, maybe we would have to bring our discussion to an end. Yeah. In the meantime, I think it's been very fruitful, you know, having everyone participating in this particular presentation. And I would love to make us all turn on our camera to take a video so that we'll be able, take a picture so that we'll be able to use it for record. So please, can you turn on your video so that we can bring you into our picture? Yeah, I can see very, very handsome and then very, very beautiful ladies also reflecting.
You are still sharing your screen.
Oh, sorry. Let me stop sharing the screen before. Oh my! No, I've stopped sharing. Let me just a minute.
Mr. Ansah, I wanted to get in touch with the Marine Department of GMET, so maybe after the meeting.
Oh, okay. All right. Yeah. So please, can you open your video so that we can take the pictures? Okay. So please, are we ready? I can see some people have turned off their video. Okay, so when I say cheese, you have to smile. Okay.
Should we say cheese? Should we say cheese?
Wait, I'm coming. I want to see others. Yes, too. Okay, so wait.
Thank you.
I'm taking it one by one. That's why. Sorry. Okay, so now for the last time,
So I see you.
Yeah, can everybody say cheese? Yeah. Okay, all right. Thank you so much. I think for now, we are done with our 17th meteorological seminar series, and we are going to make sure that we come up with another interesting one coming up next month. And you know, as you all know, we are entering into our meteorological awareness starting from 1st of March to 31st of March. So you see more of us in the media, and then we are going to make sure that people really enjoy this month. That's the month of March as the Meteorological Awareness Month. So that please, our ambassador, I can see Mr. Mr. Kweku Sintim, Ket. Yeah, this man is really my cousin. So obviously he's an ambassador for GMET, right, on various platforms. So thank you so much for participating in this webinar series, and we are going to meet next week. Sorry, next month. I can't wait for the next one to come. So we are going to meet next month for another episode. Thank you so much for participating. All right, until then, bye-bye.
Bye.